If you have a function and you want to talk about discontinuities, the only times you really have discontinuities is if you have a rational function, so you have a denominator, if you have a piecewise function, if you have something like a greatest integer function, or if you have something, piecewise function, greatest integer function, or radical. So those are really the only times. So here I'm going to factor my denominator. This factors as x minus 3, x plus 5. That is my denominator, yes? My numerator is x minus 3. It is discontinuous at x is equal to 3 and x is equal to negative 5, because that's what makes my denominator equal to 0. The negative 3's will simplify, which makes this one removable. And because this one is left and cannot be simplified, this is non-removable. It said which of these discontinuities are removable, so the answer would be this one here. Okay? As long as you write something and let me know which ones you know is removable, that's fine. Okay. The next one, I'm going to say that f of x is continuous. Continuous function, and it's never discontinuous. And then if I find f of negative 2, that's 8 minus 8, what is it? So this is negative 8, this is minus 8 plus 6, so negative 10. Yes? And then f of 1 is going to be 1 to the third minus 2 times 1 squared plus 6. So that's 1 minus 2 plus 6. 5? 4. No. 1 minus 2 plus 6. 7, 5. I was right. It's 5.
Either way.
If you don't, I don't know what to tell you. So since you go from a negative to a positive, 0, I'm going to say 0 is between negative 10 and 5.
We didn't get negative 10, but we still said it's in between.
Okay. Are there any, so we answered most of the questions, we answered the questions on the homework? Yes?
Yeah, they have their questions.
You gotta redo it.
I had a question.
Can this be? Okay, so this one, you determine infinite limits from the left and the right, which we've already done. And if you have a limit that is infinity or negative infinity, that's when your vertical asymptotes are going to occur. That's the definition of a vertical asymptote, actually. So if I'm doing this one and I have the function f of x is equal to 3 over x minus 2, and here is the graph of that for you, right here. Oh, good thing. So that's the graph. So if I'm approaching from the left, that's going to negative infinity. And if I'm approaching from the right, that's going to positive infinity. So at that point, if I thought about this, if I asked you, you would tell me that's discontinuous at 2, correct? And then you would tell me, is it removable or non-removable? Non-removable. So when you have a vertical asymptote, you have, as you approach from the left, as you approach from the right, it either equals infinity or negative infinity, and they can both go the same direction or opposite directions. And it's going to be a non-removable discontinuity. But I just want to make sure that if you're saying that the limit approaches infinity or negative infinity, your limit does not exist. You're just telling us what it looks like. Does that make sense? You're just explaining what the unbound behavior is. Yes. 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 So if I give you this graph and I ask you to find the limit as x approaches, like if I'm looking at this graph, the limit as of f of x as x approaches 1 from the left, what would you tell me? Positive infinity. Everyone good? If I asked you for the limit of f of x as x approached 1 from the right, you would tell me positive infinity. If I ask you the limit of f of x as x approaches 1, you're going to say does not exist. Let's do this one. Same discontinuity at 1, but now I'm taking the limit of f of x as x approaches 1 from the left, and you're going to tell me? Yeah, you're acting like you're bored, but yet the limit of f of x as x approaches 1 from the right is negative infinity, and then the limit of the whole thing is does not exist. Questions on any of this? That's pretty easy, yes? Pardon me?
Can you keep that screen for a second?
So the definition of a vertical asymptote is if f of x approaches infinity or negative infinity from the left or the right, then there is a vertical asymptote at that value. I could draw a picture if you want. Here's 3. If I approach infinity or negative infinity as x, so in this case my c would be 3. If I take the limit of f of x as x approaches 3 from the left or from the right, and it's equal to positive infinity or negative infinity, I'm going to say that there is a vertical asymptote. And you did this last year and I think we've already talked about this year. My vertical asymptote, I have to write it as an equation. What is the equation of my vertical asymptote? X is equal to 3, right? Yes.
What's the graph for like they're both going?
Even if they're both going up, it's still a vertical asymptote. Same thing. So let's pick a different number than 3. For some reason, I'm stuck on 3 today. So if I had something like this, then my vertical asymptote would be x is equals negative 2. Okay? Okay, so this one, determine all vertical asymptotes of the graph. That's not hard, is it? No.
Graph it, then we can mark it up.
I don't even want to graph it. When is this function discontinuous? Yes.
Yeah.
That 2, 0 just to throw you off. So this is discontinuous.
Yeah, why is 2 there?
The 2 is just there. It's okay.
Not do that on a test. You have to do that on a test, right?
When you find your vertical asymptote, you look at the denominator and you find all the places where the denominator can equal 0. That 2, if I were to take 2 times x plus 3 is equal to 0, and I use my product rule, your 0 product rule, which you learned way back in 8th grade, you would say 2 is equal to 0, and that doesn't make sense, so you basically ignore the 2. It does not bother you, and you take x plus 3 is equal to 0, and x is equal to negative 3. That 2 does not bother you.
Why would it be?
Because sometimes in life we have to multiply our denominator by 2, and it's okay. So moving on, vertical so it's discontinuous at x is equal to negative 3. It's non-removable, yes? If it's non-removable, I really don't need to graph it. I could graph it if I want to, but I don't need to, because if it's non-removable and that discontinuity is in the denominator, that forms a vertical asymptote. And you've already done this in Algebra 2, and this vertical asymptote is going to be x is equal to negative 3. Moving on. Going to example B. So when I look at this, the first thing I'm going to do is find the places where my graph is discontinuous. To find the places where my graph is discontinuous, I am going to factor my denominator. So I'm going to factor the denominator is x plus 1, x minus 1. So I'm going to be left with x squared plus 1, which cannot be factored because that's a sum of 2 perfect squares. Cannot factor that. This is x plus 1 and x minus 1. My graph is discontinuous at x is equal to negative 1 and x is equal to positive 1. Do either of those, both are non-removable. So can I just stick in non-removable? removable discontinuous, it doesn't make sense, but you know what I'm saying. Why wouldn't I factor out the what? I can't, there's nothing that'll factor, in order to factor it out, it has to be a factor. So I can't factor out these x squareds because they're both terms.
So how you put like x squared minus 1 is x plus 1, x minus 1. Why would you be numerator x plus 1, x plus 1?
This is not factorable. If I factored it as x plus 1, I would have a middle term of 2x. So if I were to graph it, I'm going to see two vertical asymptotes out -1 and 1. So my vertical asymptotes, and let's just do it for fun, shall we? Do you want to do it the hard way or the easy way? Let's do it the hard way. Let's do the limit as x approaches -1. That doesn't look like a -1. -1 from the, let's do the right. Let's not, why not? So I'm going to do from the right. So if I'm doing from the right, I'm going to pick a number that's slightly to the right of 1. So what might I use? 1.1. So I would have 1.1 squared plus 1 over 1.1 plus 1, 1.1 minus 1. If I do the numerator, it's going to be what kind of number? I just want positive or negative? Positive. If I do the denominator, 1.1 plus 1 is going to be a positive number, yes. And 1.1 minus 1 is also going to be a positive number. So I'm going to have a positive over a positive, so this whole thing is going to approach positive infinity. Do you want me to do from the left? We're good? So I'm going to have positive infinity. That's my vertical asymptote. So my vertical asymptotes, I'm going to have two. Are going to be x is equal to -1 and x is equal to +1.
Can I just look at it and see the answers are?
Yes. Shall I give you a minute? It says a rational function, determine all vertical asymptotes of the graph. So what do I have to do? I have to product sum the numerator to make sure that this x plus 4 does not simplify. 12 and 4. -12, +4. So I have a removable discontinuity at x is equal to -4.
Non-removable discontinuity at. No, wait.
There's
No, there's no.
there's no non-removable discontinuities, right?
Yeah, no.
There's like continuous because it's not, it doesn't have to denominator.
Now it doesn't have a denominator because this simplified to x minus 12. So there's a removable discontinuity x is equal to 4. There are no non-removable discontinuities. So what are my vertical asymptotes?
Continuous.
It's still discontinuous at x is equal to -4. What are my vertical asymptotes? This is a trick question. There are none. There are no vertical asymptotes.
So when there's a removable and no non-removables, then there are no vertical.
That is correct, because I can find the limit of this. If I asked you what the limit was as x approached -4, what would you tell me? Yeah. If I asked you to find the limit of f of x as x approached -4, you can just substitute that -4 into what's left, right? So that's -4 minus 12, which would be -16. Since your limit exists and doesn't approach infinity or negative infinity, you do not have a vertical asymptote. Does that make sense?
Yeah.
I'm going to pay attention to the people who are actually listening. Okay, this one. Try that one. Find the vertical asymptotes. Okay, so you factor the numerator, you factor the denominator. Can we just do everything? Yes. We have so here, I have a removable discontinuity. I'm just going to write, how's that? I'm just going to write DIS. at x is equal to -2. We have a non-removable at x is equal to -3/2. If I wanted to find the limit as x approached -2, I could do that, right? I could put -2 in to what's, because this simplifies to x minus 5, 2x plus 3. So what is formed at this -2? That's a hole. And then this is the non-removable forms a vertical asymptote. And if you were to find, if I asked you for the coordinates of the hole, you could find the coordinates of the hole too. Remember, we've already done that in here together this year, like a month ago.
That was earlier.
How would I find the coordinates of the hole? What would I do with that -2?
Plug the hole in.
Plug that -2 into here. And basically, when you're finding the coordinates of the hole, you're finding the limit. Does that make sense? You're doing the same work. I'm hoping you are all saying yes.
Yes, yeah.
Okay. Now we're going to try and do these without the calculator.
What?
Without the calculator.
Yeah, but you never calculator's not the touch.
I feel like when we do
Okay, this is, the negative sign says from the left, right?
Yeah.
So what is a number to the left of 2? 1.9.
She's like full number, so it's easy.
Quick fire.
No, you know what? We learned last time that if you go too far away from where you're approaching the limit, you may get an incorrect answer.
Why is that? That's just like the whole concept of it. Like,
No, because what
it's like everything's to the left.
we're trying to, this forms a vertical asymptote, but what, yes, everything's to the left of it, but my signs could change to the left of it. In other words, if I have this vertical asymptote here, and let's say it did something like this, and I'm just doing negative positive, if I go too far out, I'm going to get positive. Does that make sense? And I'm going to think the limit's going to positive infinity, but it's not. I want to be close to here. It is a great point, isn't it?
That's really good.
Okay, moving on.
Time to learn how to drag. Be simple.
So I'm doing 1.9. So I'm going to have 1.9 squared minus 3 times 1.9. Ooh, I may actually have to pull out my calculator for that one. Oh, no, that's going to be negative.
No calculator. It's 1.9 minus.
So this is 1.9 times 1.9, yes? So if I take that and I subtract 3 times 1.9, what kind of number is it going to be? Negative. Everyone get that? Negative. And then 1.9 minus 2 is going to be a negative. So the whole thing is going to be positive infinity. But that wasn't the graph I drew. I just randomly drew a graph. If I have my calculator, I could get out my calculator and check it to make sure I'm doing the work correctly. Yes? I'm just sitting.
Our beat's different. Our beat's different. That's not our beat.
This is saying from the right. So I'm going to pick what's a number to the right of 3? 3.1. So I'm going to do 3.1 over 9 plus 3.1 squared. So that's going to be positive. So this whole thing is going to be positive infinity.
We didn't have that one.
Oh, I just made that one up?
Yeah, wait, can I give you the one that we do have?
Yeah, give me the one you do have.
Limit of tangent of x. And x goes into pi over 2 from the right. No!
It is trig.
Number that's close to pi over 2.
What are the chances you guys remember how to graph your trig?
A number close to pi over 2 from the right is 1.7.
Huh?
1.7.
Oh, I see what you're saying. You know what? I understand what you're saying, but I kind of want to go into trig mode here for a second.
But that's going to make it so much better. The answer is going to be positive. End of discussion.
Positive infinity. Yeah, answer. We're done.
Did you graph it?
Is there any negative?
Nah, let me think.
The tangent of that has to be positive. There's no negative number.
From the right. Wait, I gotta think about my graphs. Can I think about my graphs?
Yeah, go ahead.
This is pi over 2. I'm thinking about my graphs. So when I graph the tangent, this is pi over 2. So this is the first quadrant, yes? First quadrant?
Yeah.
So first quadrant, what kind of numbers do I have?
Positive.
Positive. So,
See, this is confusing.
Oh no.
yeah, positive infinity. Yeah, I had to think about that.
Oh, where does it say?
I think it's positive infinity. Now I'm starting to question myself.
All right, let's just put that. Let's just not put it in.
Put it on the, well, I'm not going to put it on the test because I told you no trig until we get to hit the trig.
What's trig?
Let's try.
Like chapter 7, chapter 6.
Oh, that's like a semester.
That's like
Lay it down there.
All right, properties of infinite limits. So if I have f of x,
Wait, you can't graph that.
Positive infinity.
yes, you can.
Oh, you can't. It's not on my graph.
Put it down.
Okay, these are property of infinite limits. So when I do this, I'm saying f of x is going to be a function, and its limit is going to be infinity, either positive infinity or negative infinity. Doesn't really matter right now. Okay? And then the limit of this other function, g of x, is going to equal L, which means it's going to equal a number, like 2, 3, whatever.
Yeah.
Okay? So, if I go to do, oh, why did that copy over again? I thought I got rid of that. That goes away. So if I go and I take the limit of f of x, which we said was what? Infinity. And I add or subtract a number,
One.
let's say this L is 1, it's going to be infinity. Does that make sense? If this were negative infinity plus a number, it's still going to be negative infinity. Does that make? If I take a billion and I add 1, does it really matter that I added that 1? No.
yeah.
So if I take
Times one.
positive infinity times what positive 1, I'm going to get positive infinity. This will happen when L is greater than 0. Yes? But if I take positive infinity and I multiply it by a negative number, what happens? It becomes negative infinity. That's what's going to happen when L is less than 0.
Is it always just going to be
Uh-oh, now we're
Yes.
confused.
If L is equal to 0, what happens? 0.
Now we have infinity over one.
This is going away. Just ignore it. So now if I take a constant, and we're using 1, and I divide it by infinity, so if I take 1, a number, and divide it by a larger and larger and larger and larger number, what happens?
Okay, f of x is on top for us.
Okay, we'll do that one first. That would be infinity. Now can you write this one down? Because this is the one I use more often. If I have a constant and I divide it by a larger and larger number, what number am I going to get closer to? Think about dividing 1 by 2, then 1 by 4, then 1 by 7, then 1 by 0. It's going to get closer and closer to 0.
Can't like only numbers be multiple.
What?
What's like numbers you said infinity isn't a number.
Yeah, but I can approach positive infinity, meaning going up, or negative infinity, going down. I can approach positive infinity, which is a number that's getting larger and larger, and I can approach negative infinity, which is a number that's getting smaller and smaller. Like -2, -400, -4 million, -4 billion. Yes?
L is 0 for those, with the first one being 0 and the second one being non-existent.
Yes. All right, so if I give you something like this, and I ask you to find the limit, you can still follow those properties, if that makes sense. It shouldn't. So this one, if I put in 1, if I'm approaching, again, it has a plus sign, so I'm saying from the right, yes. So if I'm approaching 1 from the right, I don't know why this is on the slide now that I'm thinking about it. That would be like, what are we going to use? 1.1. So I'm going to have 1.1 plus 1 over 1.1 minus 1 plus 2 times 1.1. This is going to be positive, right? And this is going to be positive. So this is going to be infinity, right? Positive infinity. And I'm going to add 2.2. So what's the whole thing going to be? Positive infinity. That's not bad.
Yeah, that's. Graph.
Where's the graph?
We just have the big picture here.
Why don't I have the big picture? Oh, there's my big picture. So here we go. Ready? You can draw on the picture, right? Because it's on your own piece of paper. So I'm taking the limit as x approaches 1. So as I'm approaching 1, sometimes I like to do a highlighter. I love highlighters. They make me happy. So here's a highlighter. Here's 1. Yes? If I ask you for the limit of that, what are you going to say?
6.
Does not exist.
Oh, wait, yeah.
If I asked you for f of 1, yes, that would be 6.
-5.
I'll throw it off.
Does not exist.
Okay, -5. Oh, you're ahead of me. Don't be ahead of me. -5. -5 exists.
Oh, yeah, it's just those.
It's going to be 7.
Yeah. So,
Why does that exist?
because they're not.
As I'm approaching from the left, as I'm approaching from the right. They're approaching the same number.
They don't.
That would be 7, right?
4.
4.
-2.
4. The limit is -2.
And then D is just.
F of -5 is 3. And I didn't ask, but if I asked you for f of 4, what would you tell me? Undefined. And I hate to be picky about this, but I am going to be so picky. F of 4 is undefined. Does not exist. It's undefined because there is no place on this line where it is solid dot. Does that make sense? Your homework
It's a sheet here /5.
is a sheet that's on the last class and the problems on the
We don't
paper.
have any.
Wait, what?
They got erased.
Yeah, they got erased. They're not on the.
There they are.
Oh,
I've never seen